So I want to welcome you all to the Zoom session October 11 with the AAAP, and we are the Astronomy Club in Central New Jersey, and it's a great pleasure to get together tonight and talk about some things going on both in the club but also in the world of professional big-time astronomy. So as usual, we will have a guest speaker and we'll get that rolling in just a couple of minutes. I just have a couple of announcements and things to say as I show you the menu, the agenda here, the menu. After the main talk concludes, we will take a quick break. And then when we resume, we will do something novel tonight. I have a little galaxy quiz whipped up for you, and I hope you'll see why that's relevant after a couple of other slides here. And we'll get into an observatory update. And then we're going to talk really as the meeting begins to wind down. It's some important discussion that we need to have with some new initiatives. And that by that, I mean some activities and roles for leaders in the club who are going to help us as we branch into some other activities. And that includes the NASA Night Sky Network, where we're trying to embrace that to a higher extent. The idea of AAAP branded wearables, so-called merchandise facilitator. And we want to expand our presence in social media. This has been a burning need of ours for a while. Although we do social media, we need to do it better. So there's going to be some discussions at the end, and anybody who's interested is welcome to stay on. I hope that the principals will definitely be on, and we'll carry on as long as we need late in the meeting today. So there's our plan for the night. Just in case any newer members or public non-members are on board, I am Rex Parker. I'm the director. You can reach me with comments about the meetings, about the club, questions. Be welcome to your emails will be welcome at director@princetonastronomy.org. And if it so piques your interest, some of the slides I show some of my astrophotography, and you can actually find those on my personal astro website, rexparkerpixels.com. And in way of announcements, I thought it was worth bringing to your attention. Those of you who are getting Sky and Tel, you notice on the cover of the current issue, 80 years to this month, 80 years of existence of the Bible of Astronomy, Sky and Telescope magazine. And, you know, this is really a great thing to see it in its sort of new guise, where I don't know if you realize, but just a few years ago, Sky and Telescope, despite its storied history and the important role that it plays in astronomy communications and crossing the bridge between professional and amateur stuff, almost went out of business, almost went bankrupt. It was on the verge of losing its business and shutting down forever. And it came closer than most of us may realize. And it was saved in the 11th hour by a deal arranged through the American Astronomical Society, the professional organization. And that has turned into a very good thing, and now they've sort of internalized it, and there's a continuation of the original editorship and the group involved in publishing it, but the business end and the leadership behind the whole thing is now being organized through AAAS. And this is a really important thing because it probably means there's a great future for Sky and Telescope. So I'll come back to that later on tonight, perhaps, if we have a chance. But this is an example of some of the cool things you can find in Sky and Tel. Now, many of you are seasoned observers and you've been looking at Sky and Tel magazine images throughout the years, and you realize how spectacular they can be. I've never seen one like this. I had to just share it with you because this is the combination of 15 images of the moon recorded at different points throughout the May 26th total lunar eclipse. It happened to be over Australia by the amateur astronomer Joe Cowley, published in Sky and Tel in September 2021. But what's remarkable about this, the overlay of those images, you can see the Earth's shadow, the umbra. Look at how that lays itself out. That circular black region is the Earth's shadow that the moon is slipping into to create the ellipse. So you've got a real feel for the circular size, the full size of the umbra, the Earth's shadow. I've never seen an image like this. It just kind of blew me away. I wanted to share it with you, but there you go. Another announcement just worth pinging for everybody. A friend of mine sent this, and the first major city in the US passing a dark sky ordinance. And, we've talked, and we can talk later about what's going on in trying to do more to handle the dark sky, the light pollution problem. But it's notable that Pittsburgh, Pennsylvania, has passed a dark sky ordinance. Now, their idea of a dark sky ordinance, well, what it really means is they're going to try to start shielding their lights and decrease some of the wastage, but still a step in the right direction. So, well, we are amateur observer astronomers, and many of us like to get out and observe deep sky objects through telescopes, through binoculars, even with our naked eye. And this image, taken from basically a screen print from my computer with the Sky 10 running, a wide field image, 100 degrees image of the 100 degrees scale of the sky looking up. And I'm calling to your attention a couple of things, as we're getting late into the fall season now. Pegasus, the great square, is well overhead. Cygnus and all the summer constellations have moved on to the west and they're receding. This happens to be around midnight, but it's notable that right at midnight, October 15, this Friday, Andromeda, the great galaxy Messier 31, is right at the zenith. It's almost exactly overhead this Friday night. As coincidence would have it, my team is going to be running the observatory out at Washington Crossing, Team 6. And if we could just get a break on the weather, it's Andromeda and M33 and some of the real spectacular things are coming into view in perfect position as they get high overhead. And I'm mentioning this because I do want to talk about galaxies after the break. I was fortunate enough to spend some time up in the Adirondacks. My wife and I went up for a week and just actually returned on Friday. And looking up overhead, I could see an Andromeda Galaxy M31 naked eye object. There it is as we zoom in a little bit. For those of you who have to struggle with New Jersey skies, if you look at Cassiopeia, which is the W in the northern sky, well placed right now, and the great square of Pegasus, you can really figure out M31, the Andromeda Galaxy, lies almost directly between the bright corner star in Pegasus and the corner of the right side of the W. And that's a really handy landmark. Up in the Adirondacks, I could take my little 6-inch telescope. I brought my little C6 Celestron on a simple Altaz mount, and I could literally look up and sight along the top of the scope and pick out Andromeda. And this is the way it's supposed to be, the way perhaps it once was. This is what Andromeda looks like through looking at it through, in this case, a mere 3-inch telescope, my little Takahashi 3-incher, with a really nice sensor, the ZWO 071 camera recording that image, but nearly getting the entire galaxy's width into the field there, more than 1.2 degrees of angular width there. So I just want you to stare at this for a minute, and we'll come back to it after the break. But everybody remembers in Andromeda, you have two neighboring galaxies, M32 and M110, as well as M31, the main spiral of Andromeda. Stare at that for a minute and just think about what's interesting about that. And we'll come back to it after the break, and I'm going to give you a little pop quiz to see where your thinking is on all this stuff. I think that's what I have to say by way of introduction. I want to turn it over to Victor, our program chair, Victor Davis, and he's going to introduce the speaker.
It's my pleasure to introduce tonight's speaker, our guest speaker, Dr. Tansu Daylan. He's a TESS postdoctoral associate at Princeton University's Department of Astrophysical Sciences. His presentation is entitled Exoplanets, Transiting Faint Stars in the TESS Full Frame Images. The Transiting Exoplanet Survey Satellite, or TESS, is proceeding with its mission of discovering small planets transiting bright stars. TESS is able to determine the mass of these host stars and hence bulk and atmospheric characterization of the transiting exoplanets. Exoplanet searches using TESS have so far focused on bright host stars, or on specific populations of stars, young stars, for instance, Dr. Daylan has been working on extending the TESS survey to fainter host stars with a limiting magnitude of about T equals 13.5. Towards that end, he examines these faint stars' light curves to exclude eclipsing binaries, variable stars, and other factors that could be mistaken for signatures of transiting exoplanets. Preliminary results of this effort recently pushed the number of TESS objects of interest above 4,400, with a further 1,500 candidates expected by the end of the extended mission. Dr. Daylan hails from Istanbul, Turkey. He graduated from the prestigious Robert College and completed undergraduate studies in electrical and electronics engineering and physics at Middle East Technical University, METU, in Ankara. He completed his PhD at Harvard, working on constructing novel statistical models to search for signatures of dark matter. Dr. Daylan is now a TESS postdoctoral associate at MIT with a visiting appointment at Princeton University. Dr. Daylan is active in teaching and outreach aimed at communicating and advocating the scientific method across cultures and generations.
Good to see you all, and I'm very pleased to be talking to you today about our research using TESS. So I guess given the introduction, I don't need to give more context. So I will, I guess, dive right into the material of today. Let me start sharing screen and just get a quick confirmation that you can see the screen, and then we can get started.
Yes, we see.
Okay, thank you so much. So today I'll be talking about our searches for transiting exoplanets using TESS, but especially in the context of faint stars. At least that's the part that I want to come to by the end of the talk. Although I guess when you hear the word faint, and especially you being used in this context, you might first get puzzled because the design choice of TESS was actually to obtain a catalog, a legacy, in fact, catalog of exoplanets that are nearby and hosted by bright stars. And that has not changed. In fact, that's still our primary goal. However, as TESS collects more data, we are trying to exploit and maximize, essentially, in some sense, the scientific potential of the instrument. And as part of this endeavor, we have been trying to discover exoplanets, transiting exoplanets hosted by fainter stars. In the context of, I hope that throughout the talk, various nomenclature I'm using here will be clarified, as well as our goal here. So before I start, I just want to make sure that this is teamwork. I'm mostly collaborating with Michelle, who is another TESS postdoctoral associate, as well as our PI, George Ricker, the PI of TESS, and various members of the TESS team. To set the context, let's look at this figure, which essentially shows the cumulative number of known exoplanets as a function of time, which is obviously not a very recent figure. As you can see, it finishes in 2015. The story after 2015 is that we did continue to find many more exoplanets, but the generic, essentially the exponential growth that you see here is not necessarily followed any longer past the Kepler era. And this is an expected result, nothing to be so surprised about, because TESS was designed to detect exoplanets transiting bright hosts, a motivation that I will come to very soon. But basically, the message I'm trying to get across here is that we started from very few. In fact, if you just go to early 1990s, the very first exoplanet detection around the Sun-like star was the 1995 detection that received the Nobel Prize, I guess, 2 years ago now. And before that, we also had a lot of candidates, some of which even were confirmed later on to be real exoplanets. If you really want to go historical, in fact, in the almost early stages of 20th century, we had marginal evidence that white dwarf spectra were actually contaminated, but by potentially disrupted exoplanets. We can definitely say that throughout history, especially 20th century, there was mild evidence for the existence of exoplanets, but obviously that was never the scientific consensus, and it had to wait mid-1990s for this exoplanet research field, which is now a flourishing subfield of astronomy, to actually get kick-started. And by 2000s, we already had many tens of detections, and 2010s, we had the Kepler era, where Kepler behaved as a statistics mission, and we were able to find many exoplanets. So that was a big jump, even in a log plot, like the one that you're currently looking at. With TESS, our confirmed number is just around 150 now, which is not that of a great number if you think about it. But one thing that's so unique about that number is that those 150 exoplanets are all amenable to detailed characterization. So they will remain a legacy data set for many decades to come. I'm not just talking about JWST, but for the next few generations of telescopes, they will remain. And in fact, potentially you could argue that they will remain indefinitely to be the targets that are most amenable to atmospheric characterization, hence potentially characterization of planetary habitability. So this is another way of looking at it. Here you can see with different colors those exoplanets detected using different methods. And I'm going to be mostly talking about transit method here. The idea being that you have an opaque object that is transiting in front of the star, that is between the star and your line of sight. And this causes a periodic and small decrease in the total amount of light that we receive from the star. So typically in these surveys, we never angularly resolve the star, and that's not needed for transit method. We essentially look at the total amount of light that we receive from the star as a function of time, and then we do several mathematical operations. We phase fold onto trial periods, and we ask, is there a periodic transit in this time series photometric data? And these transit detections essentially come out of such large surveys and computational efforts. And that will be the main focus of my talk today. Now, why do we care? There are many unsolved problems in planetary science and exoplanet science. It's very hard to enumerate all of them, in fact, for an introductory talk like this. So I will just mention one that I really love, but there are many other fundamental problems in exoplanet science, like orbital migration, habitability aspects, space weather, things like that. But one thing that really is very striking is that if you just look at the demographics of known exoplanets, there are two main features that you'll see, especially in the context of looking at the radius distribution. One is called the radius valley. That is a valley that is carved out. If you look at the insolation versus radius plane of the known distribution of exoplanets, you will realize that there's a valley which we think is due to a process. And also there is an underabundance of exoplanets that live in the low density regime as well as high insolation regime. And we call that the Neptune desert. And we would like to understand why these demographic features are emergent. There must be a physical process behind this. And especially if you think about it, in the solar system, we have 8 planets that pass essentially the definition of what a planet is in the solar system. And 4 of them are the inner rocky planets, Mercury, Venus, Earth, and Mars. And the 4 outer ones, Jupiter, Saturn, Uranus, and Neptune, those are large planets, giant planets. And we think that they have large gaseous envelopes. When we look outside our solar system, we see examples of exoplanets that are nowhere near those 8. In fact, though in fact, the most typical type of exoplanet we find is a sub-Neptune. That is an exoplanet that is smaller than Neptune, but larger than Earth. In fact, 2 times larger than 2 times the Earth, between 2 and 4 Earth radii. And we call these sub-Neptunes. We think that they're not only terrestrial, that they do contain an increasingly larger envelope of gaseous material as the radius increases. And the mass radius relation of these is very complicated. And we'd like to understand by finding these exoplanets that are amenable to atmospheric characterization, we are trying to essentially populate this this demographics and be able to carry out tests that probe our potential models. I won't go into the details of the models because that's outside the context of today's talk, but happy to answer any questions afterwards. So starting to now move on to TESS. Here is a visualization of what TESS looks like. TESS is essentially a middle-sized NASA experiment sponsored by NASA, led by MIT. Was launched into space 2018, so it's been 3 years. And it's got 4 cameras, of each of which, well, they're identical cameras, and there are large field of view cameras. They are 24 by 24 degrees regarding field of view, and that's pretty large. As compared to other things in space that you might be familiar with, like HST, for example. HST's field of view is tiny compared to TESS. And TESS has 4 of them. So that immediately might make you think that this is a survey, in fact, a full sky survey. TESS, by changing its pointing in a systematic way, TESS is able to cover almost the full sky. In what we call the primary mission, which started in 2018, in fact, the summer. So we had a 3-4 month commissioning period right after launch. Well, first it took some time to go into orbit, which I can talk about because we are not in low Earth orbit. It takes time to do a couple of maneuvers to be launched into an elliptical orbit that is cislunar, that is between Earth and the Moon. In fact, we are in 2-to-1 resonance with the Moon, and we have an inclined orbit too. These are all design choices that allow TESS to be far from both objects, because in the deep space, when you're trying to do photometry of a large field, the object that you want to avoid for all purposes is the sun. Obviously, you want to look anti-sun. But once you do, and you're trying to carry out a systematic survey, you suddenly realize that the Moon and the Earth, in fact, Earth most importantly, because it's larger, actually come into view. So you want to avoid them as much as possible. And while doing so, we had to play some games, especially in the so-called cycle 2, when we were looking at the northern sky. So there was a garage door. Other than that, we managed to get about 85% of the full sky in the primary mission. And in the extended mission, we are almost redoing the survey with additions. This time, we are also looking at the ecliptic plane, which was something that was skipped deliberately during the primary mission. Speaking of the ecliptic plane, one thing you might remember is K2, that is Kepler after the problem with the momentum wheels, which we can come to later if we have time. One idea that I want to get across, especially to this audience, is that is essentially the answer to this question. Why do we need to go to space in order to do this type of science? Why do we need to go to space to find transiting exoplanets? This is a plot that shows the photometric precision, essentially. Let's imagine that you are doing photometry with an effective exposure time of about an hour. So the photometric precision relative to unity, well, actually, I think this is in units of ppm, so parts per million, is on the y-axis. And on the x-axis, we have TESS magnitude. TESS magnitude, by the way, is roughly a red magnitude because TESS's passband is between 0.6 micron and 1 micron. So roughly our passband corresponds to red. So looking at the stars in red light, you can try to do photometry, that is counting photons, and then you can note down your noise per object on this plane, and then you get the distribution that's shown with the orange, which is essentially just real data that we collected during sector 1 of flight operations after TESS was launched and doing science. As you can see, for a star of magnitude, 10th magnitude, essentially 10th TESS magnitude, we get a photometric precision that's about 200 parts per million. So just past that, for a bit brighter targets like 9th magnitude, we get about 100 parts per million photometric precision in 1 hour. Now, 100 parts per million is 10 to negative 4. And this is the photometric precision. In fact, if you want the radius ratio of a transiting object to that of the transited object that is in the background, that is essentially the star, that is the square root of this. So if you take the square root, that's 10 to negative 4 to 10 to negative 2. So that's about 1%. So that means if you have a sun-like star, then doing this type of photometry at about a 9th magnitude star, you could essentially find a planet of size about 1% of the star. But one thing you have to keep in mind is that not all transits are 1 hour. So sometimes transits might be might take more time or less time. And after taking into all this account, we basically can predict our yield. And one thing to also keep in mind is that smaller planets tend to be rocky, especially if we consider ourselves, if we restrict ourselves to those below 2 times the Earth radius, we think that they're more likely to be rocky than compared to, for example, sub-Neptunes. Although basically, given the radius of an exoplanet, it's never possible to immediately go to a density. So you have to also measure the mass, because the mass radius relation of exoplanets has a lot of scatter. That is, the exoplanet population shows a lot of diversity. That means there are hidden variables in the problem. That is, only measuring the masses and radii of all the exoplanets is not going to allow us to solve this problem. We will need auxiliary information, potentially metallicity of the host, potentially space weather, flare rate, and all kinds of unknowns, magnetic interactions with the star, as well as the insolation history, for example, the age of the system. These all matter. This is essentially a plot of what I just described. This is our exposure map during the primary mission. I won't spend too much time on that. And this is our ToA process. So I'm trying to now bring the discussion to what I want to focus on, or at least end with, that is the search over faint stars. But in order to do that, I have to first talk to you about our nominal process, which is called the TESS object of interest, so ToI process. ToI process collects data from various pipelines that act on the TESS data. The two most important ones are the QLP, the quick look pipeline, the MIT pipeline that takes in the data, produces light curves, produces data validation reports, essentially does all the computational methodology that I described in the very early portion of my talk. That's called BLS, box least squares. And then we do some kind of automated triage that's through a neural network, and that's called Astronet. That essentially brings down the number of candidates from millions to a few hundreds. During the nominal mission, in fact, we had about 2.5 million triggers, and Astronet brings that down to about, I think, a few hundreds. I can't remember exactly the number. But even a few hundreds is way too much for people to look at. So we also put a TESS magnitude cut. So initially in the primary mission, we said we are only going to look at things, targets, that are brighter than 10.5 magnitude. And then after that cut, then the resulting number starts to become manageable, like a few hundred per sector. And then the ToA process involved human vetters, first to individually vet data products, whether they contain exoplanets or not. And then after individual vetting is done and we collect the votes from individual vetters, we do a so-called group vetting to eventually decide whether a given data validation report points to a transiting exoplanet, or at least a candidate. Once that's the case, we put that in the so-called TOI, Test Object of Interest catalog. And so far, we have about 4,500 entries in that catalog. And a good fraction, about 30% of that, just came from our recent work that I'm going to be describing later in this talk. So here, the SPOC, an example SPOC data validation report is shown. I won't, unfortunately, have the time to go in through all the details here, but basically the idea is we look at the light curve, we phase fold onto certain important periods, and we ask, does this look like an exoplanet? Typically, if something is not an exoplanet, which by the way is a typical situation, we have a lot of astrophysical and instrumental causes for a false alarm. So we try to eliminate these by essentially checking a couple of metrics, like whether there's a so-called centroid offset. That is, if the light curve's difference image, that is the center of mass during the transit and out of the transit, moves with respect to each other. That's a centroid transit. That means that whatever we triggered on is not on target. And that typically is evidence that it's a so-called nearby eclipsing binary. Now, one thing I have to just mention is that in the universe, there are many more eclipsing binaries than planets. Planets' occurrence rate is much lower compared to eclipsing binaries. I'm talking about stars that occult each other. And that means because of this relative drop in the occurrence rates, we cannot just go and say, you know, all the nice triggers that we are getting are exoplanets or even just candidates. We can't do that. And at best, the candidates that we get are only tentative candidates that need to be followed up because of this confusion or blending that is caused by large test pixels, which is something that I forgot to mention earlier in the talk. But test pixels are large, nothing compared to what you're used to in amateur astronomy that is from ground, because ground-based telescopes typically are able to oversample the PSF, the point spread function, where the point spread, well, we don't actually care about the point spread function in ground-based observations. We care about seeing, and you can well resolve the seeing because you have the capability to do that. In TESS, that's not the case. In TESS, our PSF actually it looks very different. On axis, we have an almost undersampled PSF, and off axis, the telescope is not focused, so we actually have an oversampled PSF. And doing photometry is not obvious, so you really have to know what you're doing when you're doing photometry with the TESS targets. Now, I don't have much time, but I just want to quickly mention a recent result from the TESS mission before I go to faint targets, because this is not a faint target. In fact, it's one of the brightest targets on the sky. In fact, the third, if you include all the targets that contain at least 4 transiting exoplanets. And if you only consider sun-like stars, like G-type stars, then this is the brightest target on the sky that contains at least 4 transiting exoplanets. In fact, thanks to a recent paper, a follow-up detection by KEOPS, we now think that there are 5 transiting exoplanets in the system. It's so called TOI 1233. It's HT Henry Draper catalog ID is 108236. And it's one of my favorites from the TESS mission. Although I worked on various targets, which are all high impact, this particular one is unique in the number of planets, transiting planets that it contains, allowing us, at least future generations of near future generations of astronomers, to do comparative studies of exoplanet atmospheres. And unfortunately, I don't have much time to discuss the system, but it basically looks like this. If you had an infinite angular resolution, which we don't, actually, I just lied, it doesn't look like this. We only look at the light curves, but when we invert the light curves, we can infer that there are planets transiting the star. And this is actually not a black hole, sorry, that was a pretty bad choice of color scheme. And this is how it looks in our data, the ToA 1233 light curve. Each planet's transit is color coded differently. And when we phase fold, we get these nice box-shaped periodic transits that nicely phase fold. And then we can infer properties of the planet, such as their radii. Here, in fact, you can see the radius valley that I just described early in the talk. And one of the planets happened to be very close to that gap. And we can also start studying their compositions, although, as I said, there's a big uncertainty on their masses once we only know the radius. And COVID situation, unfortunately, did not help with the follow-up of these targets, especially in the south. The Magellan telescopes were closed for a large fraction of last spring, and ToA 1233 is a spring star, so we couldn't actually observe this target for a long time, and its mass measurements are lacking, or at least lagging at this point. And it also allows us to study the fundamental plane of exoplanet atmospheres, the equilibrium temperature versus radius. As you can see, the planets in the system extend over a large region. And let me skip this part because I actually want to get to faint stars as soon as possible. So I've discussed already that we have, well, yes, maybe I didn't say, but we have about 4,500 known planets if you just check the NASA Exoplanet Archive. So you might ask yourself the following question. What do we actually gain by finding more planets? Like, once we have a statistically meaningful distribution, what is there to gain by discovering more? Well, whenever you look at a distribution and do any kind of anomaly detection, there's always going to be rare samples because these planets live in an n-dimensional space. They have n-dimensional features. They have radii, effective temperatures, ages, metallicities, densities, etc. So this is a big dimensional space. And in this space, there's always some rarity with respect to some definition. And that definition sometimes happens to be correlated with our fundamental problems in planetary astronomy or planetary science. So a couple of examples are young systems or systems where there are planets in the Neptune desert that we think that shouldn't exist. And we would like to find similarly rare systems. And on top of that, we also want to study the occurrence rate of exoplanets as a function of those. And for that, we need to be able to bin the exoplanet distribution in these features. And for that, we need a lot of statistics. And that's not an easy task. So we need to find many, many more of exoplanets. Now, I've already talked about the ToA process and that it goes down to TESS magnitude 10.5. And out of the about 4,500 ToIs, we have about 300 known planets, and about 700 of them are already false positives that they have been followed up and shown to be either eclipsing binaries or instrumental noise or something else. And if you just think about it, as you go fainter from 10.5, you get about a factor of 2 increase in the cumulative star count. So basically, by going 3 magnitudes fainter, we get a 8 times larger population. And if you go down to 13.5, you get about 20 million targets, and that's a good number. In fact, as I was saying, we go from millions down to a few hundreds in Astronet Output, and we wanted to basically bring this number down to a few thousand. In fact, it happened to be 1,617 for the primary mission, as a catalog of planetary candidates. And again, I don't unfortunately have time to go into technical details of this, but we basically employed traditional cuts on our data validation reports, and we basically tried to get rid of all obvious eclipsing binaries or sources of stellar variability or on-target eclipsing binaries whenever we can. And some examples that came out of this search is, this is a planet candidate, as you can see, the light curve and the phase folds. And on the right, you see also the image relevant. And one thing that's another example that is a false discovery, or at least false positive, is shown here. Again, unfortunately, maybe we can go back to this once we have time to discuss during the questions. But coming to the results, let me mention that the typical brightness of the targets that we triggered on, or so-called in technical or TESS lingo, it's called alerting. We alert the ground-based astronomers about these TESS objects of interest. The one thing that strikes out about these targets is that they're faint. They're faint about, I'd say, 2 to 3 magnitudes, and that's a design choice. And here the x-axis is the ToI ID, which acts roughly as a time axis, but not necessarily so, because we tend to alert things basically as an ascending number in ToI. So later ToIs also are alerted at a later time. But sometimes there are a couple of, I guess, exceptions to that rule. And you can also see that RToIs, which again correspond to roughly between 2,500 and 4,400, they're also slightly farther away from our solar system. And that's also something you'd expect because they're fainter. So on average, they'll be farther out. And another thing that we can say is that we also tend to trigger on shorter periods. And that's expected because we are working with worse data. The data quality at fainter magnitudes is degraded. As a result, we need more transits to make sure that we can actually get a good planet candidate. So our period distribution is also skewed to lower values. And the transit depth here on the y-axis is also skewed up, and that's also expected because the photometric precision is worse for these targets. So we are essentially trying to account for that by triggering on transits that are deeper. And finally, the radius of the planet's radius distribution is also skewed higher. And that immediately follows from the previous plot, because if something is deeper, that also means it's larger. If the transitor is deeper, then it's if the transit is deeper, the transitor must be also larger at fixed host radius. And that's also what we see. In fact, about half, in fact, more than half of our catalog is actually made up of hot Jupiters. So we indeed, we think that we are making a big contribution to studies of hot Jupiter occurrence rate through this work. And unfortunately, I don't have time to discuss these all, but let me just jump to conclusion. And if I have time, I'm happy to get any questions. So at the end of today, and sorry for the typo there, we have alerted 1,617 new TESS objects of interest, TOIs. And this is only through the primary mission. Now, we have an ongoing work that is extending these results to the extended mission, which also includes the southern, the northern hemispheres, ecliptic hemispheres, as well as the ecliptic plane. So we are indeed very hopeful that the extended mission results will return a similar number of TOIs and similarly interesting population of TOIs. And using these, we aspire to eventually be able to do a complete occurrence rate study based on the TESS data, which was not a design choice. In fact, as I said, let me just conclude the talk by referring back to what I started saying, which is that TESS was basically designed to be able to do high precision photometry of nearby bright hosts so that we could discover small exoplanets. However, a byproduct of that is being able to, especially with the availability of so-called full-frame images, we are now able to extend this type of search to many more targets, in fact, 20 million host stars. And despite the fact that most of these are not going to be amenable to detailed characterization like mass measurement or atmospheric characterization, they will still indeed be very useful for our investigations of occurrence rates and demographic properties of exoplanets. With that, let me conclude. Again, thank you all for listening and happy to take any questions.
Okay, well, I think we have plenty of time for questions, and I'll start really the first one. I was interested when you're talking about eclipsing binaries, trying to ferret out eclipsing binaries as false alarms, false positives for transiting exoplanets. I mean, really, as you decrease the mass of the binary star, it essentially becomes a transiting exoplanet at that point. Do you have like a threshold where an eclipsing binary is no longer an eclipsing binary, but it is in fact a transiting exoplanet?
Mm-hmm. Well, when it comes to distinguishing between eclipsing binaries and planets, one thing we have to keep in mind are brown dwarfs too, because when we look at the mass radius distribution of exoplanets, brown dwarfs, and in fact, if you want to include compact objects like white dwarfs that are essentially being supported by only degeneracy pressure, and main sequence stars, which we know burn hydrogen into helium. And in fact, if you want to be complete, you can also include giant stars that don't necessarily burn hydrogen, but heavier elements. They all live as a continuous distribution on the radius mass plane. And the exoplanets and brown dwarfs and essentially white dwarfs, they draw a continuum, essentially that looks like a inverted U, that it goes up and then down. But stars are an outlier because they're supported by energy that comes out of the fusion process. So when we try to distinguish an exoplanet, in fact, a large exoplanet, I'm talking about Jupiters, and brown dwarfs and stars, it's not possible at all to do that just based on the radius. And unfortunately, with TESS, that's the only piece of information we have. We can only, well, I mean, in addition to auxiliary transit properties, which I can talk about next, but we only know the radius. Without mass, it's hard. It's in fact a degenerate problem. The unfortunate thing is that the lower tail of the stellar radius distribution extends well into the upper tail of the radius distribution of exoplanets. So there's basically between about 10 Earth radius and about 25 Earth radius, brown dwarfs, exoplanets, and stars coexist with certain tails mixing into each other. And what's complicating that is insolation, because when these are binaries, exoplanets are so-called inflated due to thermal energy that they receive from outside, from a heater nearby, like a star. So as a result, an exoplanet at a given mass can have a lot of different radii too, depending on its insolation. So there's a couple of things all acting at the same time, and it's almost impossible to just do that type of distinction based on radius. So as the TESS team, we don't have control over that. So as long as the radius is consistent with planetary nature, and for that we typically look at the insolation and radius plane. As long as that value is still within the reach of the known exoplanet population, we still keep that as a planet candidate. And we let future follow-up people worry about that question of whether that's actually a massive star or a massive brown dwarf. So we know that brown dwarfs are the massive counterparts to exoplanets, hence they have some deuterium fission in them. And then we have even more massive objects called stars that we all know and love. So in terms of mass, there's a big distinction, but not in terms of radius. Now, I made a pointer, let me finish that, which is that from the TESS light curves, we do get some more information than just radii, which is transit properties. So we know, for example, the shape of the light curve. Now, the shape of the light curve tells us one thing, which is, or at least the probability with which we obtain the shape of the light curve. And that is basically the relative size of the transitor and the object that is transited, the background object. If you think about it, if the sizes of the transitor and the background object are comparable, it's more likely for you to get a so-called V-shaped transit, a transit with no flat bottom. Whenever the size of the occulter or the transitor, whatever you want to call it, refer to, is much smaller than the host star, then it's statistically much more likely for it to have an inclination that it would transit closer to the equator, and hence it would result in a U-shaped transit. So if you typically see a V-shaped transit along with a very large radius, we typically rule that out immediately as an eclipsing binary, because it's very statistically unlikely that that's to be coming from a planet.
Okay, just when you were talking about, I'm not sure I remember the number, ToI 1233, when you were showing the light curves on that, you sort of very helpfully colored them, you know, the colors of the planet. Can you show that again? Because it's not,
sure.
To me, if you don't, it takes a lot of imagination to see a light curve in that. I just, it seems very challenging, very, very challenging to detect a transit in there.
Right. So we don't do that by eye. So that's the important takeaway message here. Because if we were to do that by eye, our eyes cannot do the operation of phase folding. Unfortunately, our eyes are great in picking up so-called local features. In fact, we have, for example, we have citizen science projects called Planet Hunters TESS, where people, in fact, they don't need trained eyes for that. They just look at time series data, and then they can immediately tell if something looks like a transit. Now, the problem with that approach is that our eyes don't have the ability to phase fold unrelated chunks of light curves to tease out an otherwise very low signal to noise features. And that's what we achieve by using the methodology called box least squares. Essentially what we do is taken, essentially given a time series data set, we define first a period grid over which we want to search. That is, we can start, let's say, from 0.5 days, half a day, so 12 hours. And we can go up to, for example, well, it depends on our temporal baseline, but based on what we are currently looking at, for example, this extends at about 60 days. So you could say, okay, I'm going to search for periods up to, let's say, 30 days or so that I get like 2 transits at least. So you can say, okay, I'm going to search over a trial grid of periods. And at each period, you phase fold the time series by using the modulo operation to basically do the phase fold. And then on the phase curve, you search for a dip that has an arbitrary duration. We call it the duty cycle. Essentially, it's the amount of phase that the desired feature extends in the phase curve, so between 0 and 1, and also with arbitrary epoch. So the feature could be anywhere on the phase curve. So we do this, and this is a very time and compute expensive, I guess, operation. But at the end of the day, it is doable. We have fast algorithms that we can use for that. We also use GPU programming sometimes for that. And at the end of the day, once we do that, we are able to tease out these features. Now, looking at this light curve, you would probably be able to, your eyes would probably be able to pick out, I would say, E and D, but probably not C and very likely not B. But basically, algorithms like this do the phase folding very efficiently and allow us to look at spectra. And in those spectra, we look for peaks after doing some post-processing on the spectra.
Well, when you say phase folding, I don't know what that means exactly. Could you explain that term?
So phase folding means that given a time series, you say, what would happen if I would do an what would happen if I were to operate on this time series with the modulo operation? That is, you divide it by the trial period, and then you take the remainder and you basically bring it to the beginning of the time series, and then you do that again. So you find the remainder and then bring it back to the beginning of the transit. So basically, that's the remainder operation for millions of data points. At the end, a phase curve is a series, not time series, but now it's a phase series where the x-axis loses its time meaning, but rather we call it so-called phase. Phase can only be defined with respect to a periodic event, and then you have a trial period, it's that period essentially. If you're, for example, searching for periodicity at 10 days, it's the phase curve for 10 days. So a phase curve is only meaningful with respect to the period over which it's been folded. But sometimes we also need to compare different phase curves at different periods. For example, we like to compare the subharmonics and the harmonics, because if you have strong power at a fundamental frequency, you also need to have consistent powers in the subharmonics and the harmonics, because if you phase fold a time series at 20 days as opposed to 10 days, you will still get some power, residual power.
Okay, I want to encourage a few other people to ask questions here.
Oh, yeah, I have one. If this question was already asked, forgive me, because I have to leave the Q&A for a short while, but will the future mission of TESS be revised based on the findings of the James Webb Space Telescope?
No, actually, it's the other way around, I would say. TESS is a precursor to JWST. It's been designed so that we would have the targets available by the launch of JWST, and quote unquote, thanks to the delay in the JWST mission, we were in a better position to make sure that's the case, because our targets are going to be observed by JWST, and it's not practical or necessary to try to modify the survey strategy of TESS based on the output of JWST, because JWST is a follow-up instrument. It's not a survey. So typically we don't modify surveys based on follow-up. Instead, we try to follow up things that were discovered in surveys.
So it's true that TESS is actually a finder scope for the Webb. Okay.
Yeah, that's precisely true. One thing I would say is we might still change in future extended missions. We might still make changes to the way we observe the sky using TESS, and that might still get some contribution from an increasing knowledge of the sky. For example, we have Gaia operating, and it's been collecting high precision astrometry, so positions on the sky, for example. And we also have many other instruments. So it's not impossible to at least partially motivate a survey strategy, given the increasing amount of information. But I would say it won't work in the way of JWST telling us what to do. It's actually the other way around.
Mhm. Thank you.
I'm curious about why the choice was made to image in the red and near infrared.
Right. So that's a great question. And it's a design choice, a deliberate one, because TESS is a mission that has a certain theme. And that theme is M dwarfs. Because M dwarfs, post-Kepler, M dwarfs were the population of planets where there had not been a rigorous large-scale survey for transiting exoplanets. And there's actually a big motivation for doing so too, because they are smaller stars and their habitable zones are actually much closer to them, which means that you can find habitable zone planets by observing the targets over a much shorter amount of time compared to Kepler. So Kepler's design goal, which unfortunately was not met, was to discover Earth around the sun. For reasons we know, due to that led essentially to the K2 mission, that was not fully met, although there was a big improvement on our statistical understanding of exoplanets, and we almost got there, but not quite. And TESS was designed with a different philosophy, not to reproduce Kepler, but to explore the transiting exoplanet population around smaller stars. Now, smaller stars also happen to be redder because of the fact that these are smaller, and the amount of thermal energy that comes out because of the fusion is not able to make them glow orange or yellow, but rather red. So by skewing our passband to redder wavelengths, TESS was able to optimize its mission of being sensitive to habitable zones of smaller stars, low mass stars. So that was a design choice.
Thank you.
So, I mean, we're all interested in mirror Earths, so to speak. So how close is TESS to being able to detect, say, an Earth-sized planet around a sun-sized star?
So in terms of the total amount of small planets, we did in fact find quite a few. But one thing we excel in is that population is the relative potential of further characterization is much greater compared to previous surveys, because the typical so-called super Earth that we find is more amenable to atmospheric characterization than this typical super Earth that was known pre-TESS. But you said something that actually has a keyword in it. You said Earths around the sun-like stars or suns, and that is a very hard problem. And that will have to wait for Plato. Plato is a mission that is going to try to pick up where Kepler left, and they will have a larger field of view, many more cameras, and slightly better photometric precision. So in the same sentence, I made comparisons to Kepler's and TESS, so I have to decode that. So compared to Kepler, it will have a larger field of view, and compared to TESS, it will have many more cameras. And photometric precision-wise, it will be also better than TESS. So it will try to have a baseline that is long enough for us to find Earth-like planets around Sun-like stars. But that is an endeavor that takes a lot of time and patience. And we also have to, it's also an engineering, I think, success, because we have to make sure that the spacecraft is very robust to any problems, so that we can have continuous baseline photometry for many years, in fact. And that's the requirement to be able to find Earths around the suns. But there's also the motivation that even though Earth around the sun is the only data point that we have with respect to habitability, there might be other parameter spaces, I guess, or chunks of parameter space that is just as amenable to habitability or life. And TESS was basically an answer to that question, or to that investigation. There are arguments against white. For example, M dwarfs can be habitable because when you're so close to the star, you're also in the tidally locked region. So that means that you're showing your same face to the star at all times, and that increases the day-night temperature contrasts, and also causes a lot of atmospheric escape from the day side. And as a result, a terrestrial planet could just lose all of its atmosphere. Even a strong magnetic field maybe could not save it from that fate. So M dwarfs, low mass stars, are interesting. They also flare a lot, and we think that flares may be, in fact, an ingredient, a required ingredient of life, may or may not. We just also don't know. But if so, M dwarfs might, in fact, be both the originator as well as the killer of life. And it's an intricate trade-off that we have to play. One thing that's interesting about M dwarfs is that there's so many of them. So in fact, about 75% of all the stars in our galaxy are low mass stars. As a result, we have to also appreciate the in-class diversity of these objects, and the fact that even if a given process is extremely rare, having some 75% of your 200 billion stars in the galaxy and being M dwarfs, even a very low probability event could have arisen just because of the sheer number of such systems.
So if there isn't somebody waiting to ask a question, I will ask one. Victor, can you tell if there's anybody else?
Hold on, let me check the chat. I don't think so.
Well, so I'll go ahead.
Go ahead.
This is really, I don't want to plague you with a difficult answer, but really just a simple one. Is there any evidence in your light curves that you might see something suggestive of a protoplanetary disk, or would that be too homogeneous and you couldn't really see anything in the light curve at all? And just a second follow-up to that, we get all the time in our outreach the common question: if you were to think of all the stars in our galaxy, based on what you know right now, what fraction of them have a planet or planets? Just in a general sense.
Right. So let's see. For the first question, the circumplanetary disks. Did you ask about
protoplanetary? Protoplanetary.
Yeah. Okay. So protoplanetary disks, I would think that would be a very hard science to do in optical, in red passband, because if you're looking for protoplanetary disks, you want to go much redder, in fact, into far infrared, where that type of dust would glow and give you a much better contrast. If you're talking about the occultation properties of such objects, we do get a lot of crazy light curves, and sometimes it's not immediately possible to point to a particular process, but we have random transitors, we have weird dips around certain stars. And typically, if they're really young, we just wave hands and say, like, I don't work on that type of science, so I haven't followed up any. Although I have ongoing projects to look for circumplanetary either megastructures or natural rings like our Saturn or similar occulters that are not necessarily circular. We can look for things like that indeed. Now, with respect to your second question, we think that the occurrence rate of exoplanets is about roughly about 1%, give or take.
1%?
Yeah, like a few percent, I would say. And one thing to keep in mind, though, is that the occurrence rate of transiting exoplanets is downgraded by the transit probability, and that is not taken into account when we quote these occurrence rates. By the way, when we say that a few percent, I'm actually referring to the large exoplanets that we tend to find with TESS. If we talk about smaller planets like Earth-like, they may just be something like 50%, by the way. But there are very big uncertainties when it comes to such small transiting exoplanets, when it comes to such small exoplanets. But the usual consensus is that it must be as large as 30% or so when we are talking Earth-like. But one region of the parameter space that we know very well are hot Jupiters, and for that it's about 1% level. Now, it's also important to realize, by the way, that TESS is not a great contributor to this type of science, despite all our efforts with the faint stars. And that's essentially because, maybe I already said this, but let me emphasize, it's because of our large pixels. So we are not able to statistically validate most of our candidates, which was something that Kepler was able to do, because Kepler had much smaller pixels, and they were able to just look at a pixel, look at its centroid offset and all kinds of light curve features, and just based on the potential number of blended objects, most of the times they were able to statistically validate a given threshold crossing event. And as a result, they were able to discover many more exoplanets, which then evolved into much better demographic studies. With TESS, we don't have that expectation because our large pixels will never allow that. But we still are going to be able to make contributions in ways that Kepler couldn't. For example, TESS is able to do this across the full sky, whereas Kepler was looking at a particular field, so it wasn't sampling the occurrence rate over the full sky, whereas we are able to do that. So it's a whole different regime that we are contributing to.
Thank you.
Yeah, I have a question. If you found a planet, I mean, I guess you didn't find any planets that are Earth-like, I suppose, yet. That's correct?
Yes, with TESS.
Okay, that answers one question. The other, I mean, are there protocols in place if, supposing you found an Earth-like planet and you're able to tell by, I don't know, the chemical composition of the atmosphere that it's artificial being combined or artificial life? Do you have protocols in place? How is that released to the public?
Right. So let me just clarify one thing. When you say Earth-like, I actually mean in the space of all relevant features, such as equilibrium temperature, radius, and mass. We do have candidates that are as small as Earth, but not necessarily at the same insolation. Or we have things, for example, we have candidates at the habitable zone level, but not necessarily as small as Earth, or not at the same mass or something like that. Basically, in the search space, when you restrict to all relevant features, Earth is very unique, in fact.
Sure.
Now, with respect to protocol, I think with TESS, we are kind of relieved from that stress because it's unlikely for us to find a habitable Earth. TESS is not necessarily designed for that, although we might get surprises as the data set increases and we become more and more sensitive to smaller signal to noise events. That might change in the future, but so far we haven't had that problem. And let me also just make it clear that basically figuring out something about an exoplanet to the extent that to think that it has definitely life, or even let's say likely have life, that's not going to be an overnight task. It's not going to come easy. It's not going to be like we look at the light curve and suddenly realize that it has life, because there are many indicators of life, but there are also many false alarms. So the scientific community, I think, is always going to be very careful in carefully assessing all kinds of evidence. So just for example, seeing oxygen which you'd think as a biomarker, for example, in the atmosphere, that's not going to, obviously it's going to make headlines and all that, but it's not going to convince all the astronomers and all the researchers in the field right away, because we know that nature is very smart, that it can outsmart us. So we just need to be very careful in assessing all kinds of false alarms. And that's ongoing work. That's not a well-answered question. In fact, the question of habitability and what it means for a planet to show signs of habitability, we call these biosignatures, is very, very hard, in fact, to write down at this point. In fact, I would say that technosignatures are much more evident, smoking gun signatures, than biosignatures, at least. But then technosignatures make more assumptions, like you have to have, obviously, planetary conditions, then it has to produce life, if the life has to evolve to the extent that it can produce intelligence, and that intelligent life has to just not kill itself until it can produce the technology that it then uses to communicate to us, etc. And then there is also the just choice of whether they would choose to contact us, and that's a big if too. So that there are many assumptions there.
Maybe not purposely try to contact us, but if we could pick up artificial life, or light, that type of thing, or their radio communications, we still could assume that there'd be civilization, not that they're trying to send signals out to necessarily contact us.
Right. One thing to keep in mind when it comes to SETI is that we are in a phase of our technological evolution which is extremely transient, because we just started emanating radio waves into deep space like a century ago. And a century later, we might have technologies that actually just reduce the total radio output, either indirectly or on purpose. And with respect to cosmological timescale, obviously, a few centuries is just nothing. So you don't necessarily integrate the number of civilizations when you integrate Drake's equation to find this. So the delta T term is extremely small when it comes to current contemporary time. So we should not be making extrapolations based on our current state of technology. Other civilizations might have wildly different choices or priorities or technologies that might occult, not using things that are beyond physics, obviously using laws of physics, but just in using technologies that may not be available to us at this point.
At this point, we can't even tell if there's life next door on Venus.
Correct.
And that doesn't even bring up intelligent life, which we can't tell if there's any on this planet.
Yes, that's.
I have a couple of questions.
Yes, please.
One, how far out have we seen? How far away have we seen exoplanets? What's the farthest out? What's the closest? And the second is, are there any, to continue the discussion that was begun, are there any effort to at least identify this one might be a possibility that there might be life on it, or even if it's just some vague sense that there might be a candidate for a planet that might support life? Are there any of those that have been identified so far?
So with respect to your first question, the closest one I would say, I think, is Proxima Centauri B. And the
That's
farthest one, sorry?
That's what, about 3 light years? Or?
Yeah, like 1 parsec-ish, just outward of that, I think. And let's see, the farthest one, I don't know by name, but I think that must be a micro-lensing planet, because each detection technique comes with its own selection function. And transit method, and also let's also take into account radial velocity method. Those two are highly skewed towards massive, large, and also short period planets. So when you go farther out, and also that means, sorry, one more thing. They also require bright hosts, at least bright enough for us to detect using TESS. So that also means that the targets are nearby. In fact, TESS, with respect to that, is extremely close. Typically, we look at targets around like 100 parsecs or so. Kepler was better. Kepler was like a few times farther out. But microlensing planets, which obviously we don't have the ability to characterize in detail, we only know their masses and some vague characterization of their orbital separation, they can be detected very farther out because of the fact that they in fact require the lensing signature. And in order to do that, you actually need to look at very far background objects and kind of in the middle lenses, which are essentially a pair of a star and a planet that's in orbit around it. So we can find like planets up to a few kiloparsecs using that method. And that, I think, one of those must be the farthest out one. Now, with respect to your second question of whether we think that there is substantial evidence, and substantial evidence, I'm using that as understood to mean basically beyond tentative, like hand-wavy arguments about habitable zones or flare rates and all that. I don't think we have substantial evidence. I'm not saying like complete evidence, or I'm not saying like 90% evidence. I'm just saying substantial evidence. I don't think we have substantial evidence for planetary habitability for any planet. We have metrics that define the proximity to Earth, and that can be interpreted in some way as being close to being habitable, but I think there's a big if there. So if you just define a metric that takes the difference between the radius of an arbitrary planet and Earth, and then makes that a factor, and then do the same for mass, do the same for equilibrium temperature, do the same for effective temperature of the host star, do the same for, let's say, metallicity. You can just determine, like cook up a metric that then ranks your planets with respect to that metric, and say you can probably get a couple that look very similar. As I would guess that those would come from Kepler because of the equilibrium temperature and radius requirement. But even then, for those planets, I don't think we have substantial evidence because we don't have biosignature measurements for those. And we don't even know what's a good biosignature to actually search for at this point. Like, people have tentative ideas, but I'm sure that tomorrow, once we actually are able to get that data set and some people fit it, I'm sure we are going to argue amongst ourselves as to whether something is real, whether there's any false alarm to any of these biosignatures. So even then, I don't think it will be counted as substantial evidence. Maybe after some couple of years of internal discussions in the exoplanet field, maybe.
Okay, thank you.
Thanks.
Quick question, did you find any moons by any chance?
Not yet. I have searches for transiting exomoons using TESS. We have basically just mild candidates, but nothing to get too excited about. And I think TESS is a little, I guess, behind Kepler in our ability to do this type of search, because when it comes to exomoons, at least when you search for using this transit method, you really want high precision, photometric precision. And TESS is not at fixed magnitude. TESS is not the instrument to do that. It's Kepler. So I think given that, oh, by the way, I mean, Kepler does have a candidate. I think, was it 1625? I mean, don't quote me on the numbers, but it might be that. But there's one strong candidate, I would say, from the Kepler mission, but there is no consensus on it yet in the exoplanet field. So we don't still count it as a confirmed planet. I think what needs to be done is have a couple of candidates, and once that happens, I think those strong candidates will start becoming confirmed exomoons, but we are not there yet.
Okay, Dr. Daylan, thank you so much for a very interesting and obviously question-provoking presentation. Thank you very, very much for being with us tonight. Rex?
Yes, thank you. That was brilliant, and we thank you for spending time with us and enlightening us on your research. We wish you the best of luck going forward. We'll keep an eye out for you.